I'm Anil Kumar. Welcome to my series on calculus. We'll talk about how to evaluate limits when we are given indeterminate products. We have already seen that L'Hopital's rule can be applied to all the situations where we have indeterminates involved. So most of the time when the case is 0 by 0 or infinity over infinity, we successfully get a result using L'Hopital's rule. In this particular video, we'll consider another important indeterminate, which is products. When I say products, we'll talk about something which is 0 times infinity or infinity times 0. Now what do I mean? I really mean that if we have two functions, let's say we're trying to find limit of the function f of x as x approaches a, and let's say this is 0, and if there is another function g of x and we're trying to find the limit as x approaches a for g of x, and that is equal to infinity, for example, in that case, what is the limit when x is approaching a for f of x times g of x, right? This is what we're trying to figure out. Now we are not very sure whether it will be 0 or will it be infinitely large or it will be somewhere in between, right? So that is what we are saying is 0 times infinity, correct? So those are the cases. A general method to solve this is kind of like this. So the general approach will be that we should write this in the form of a 0 by 0 or infinity over infinity. So what we are going to do here is that when we try to figure out what is the limit as x approaches a for f of x times g of x, we could write this as limit x approaches a of, let's say, f of x over 1 over g of x. So as soon as I do this, right, so what really happens is that we get a situation which is this was approaching 0, so this is 0 over 0 situation. So in this case, we'll now apply the L'Hopital's rule and get our solution. So that is the approach, right? Now, for some of you, it may be of interest to understand why, after all, 0 times infinity is indeterminate, right? So let's also look into that question, why 0 times infinity is indeterminate. Right. So, and after that, we'll take up these examples where we are going to apply this approach to get the limits. Perfect. So let's look into this question. It's very interesting why 0 times infinity is basically undefined. So, well, you could reason out that, well, 0 times infinity could be equal to 0, right? So that is possible, right? Is possible. So let's say it is true, right? Let's say it is true. Okay. So in that case, I could always write 0 as 1 over infinitely large quantity. So what we get here is that 1 over infinitely large quantity times infinitely large quantity is 0. However, we know that a number divided by the same number, I should say, let's say if I have something, right, something divided by something should be equal to 1, right, because that's the same thing, right? But what do we expect? We expect infinitely large over infinitely large to be 1, correct? So what we see here is there is a contradiction. There is one thing to look into, right? So it is a contradiction. And therefore, we know that this is an indeterminate, right? So this implies that 0 times infinity is indeed an indeterminate. Perfect. So just as we proved why 0 by 0 or infinitely large over infinitely large quantities are indeterminate, right? So similarly, we have this situation. Perfect. So let's move on with the examples now and see how to find these limits. So here is our first example. We'll evaluate limit as x approaches infinitely large number for x square e to the power of minus kx. So let's try to understand the graph also of this. So if I sketch the graph for x square, then we get something like this. Correct? And if I sketch the graph for e to the power of minus kx, so minus means decaying, so it will be kind of like this. Right? So what do you notice here? You clearly notice that one of them is approaching infinitely large value, the other one is approaching 0. Right? So when I substitute infinity here, we get a situation which is infinity times 0. So that is the indeterminate product which we are talking about. So I hope the situation is clear to you. So the strategy here is to convert this and write it as what? So let me write down the strategy which we are going to follow. Strategy is to write as a rational function. Correct? So we'll say, let this limit, when x approaches infinity, for x squared times e to the power of minus kx, we could write this as limit x approaches infinity. While minus indicates that it is better to take the second term in the denominator, so we get e to the power of kx. Now if you look at it, then what do we have? The situation now is that if I substitute infinity here, we get infinitely large thing on the top, and infinity there will also give us infinitely large thing. So this is a candidate for L'Hopital's rule, correct? So to find this limit, we'll now apply the L'Hopital's rule. So I'll indicate this using the letter H. So that means what we're trying to do here is basically writing the derivative of the numerator and the derivative of the denominator, right? So what we get here after applying the rule, we get this as limit x approaches infinity. Derivative is 2x for x squared, and the derivative for this will be k times e to the power of kx. Correct? Okay. Now again let us check. If I substitute infinity in the numerator, I get infinitely large value, and here again we get infinitely large value. That means we can once again apply L'Hopital's rule and then find the limit. So we get limit x approaches infinity, and the derivative of 2x will now be 2 divided by, here we get k squared e to the power of kx. Well, now in this case, if I substitute infinity here, what do I get? Now in this case, if I substitute, I get this as equal to 2 over infinitely large quantity, correct? That's what we get, which is not an indeterminate, which is definitely 0. Which is definitely 0. So the answer for this limit is that the limit for the given function as it approaches infinity is equal to 0. Is that clear to you, right? So that becomes our solution. And if you analyze the graph, we know and we understand that exponential functions are much faster, right? So we know exponential functions decay or grow much faster. So it makes sense that the effect will be mainly because of this, correct? So we were expecting 0. Now this is very important to understand as we move along, and the reason is what? The reason is the trend, and the trend is towards multiple choice questions, right? So I like you to, while we are solving these questions, to understand why did we get this result, and if I'm given a similar situation in a multiple choice question, then how could I answer it within few seconds? That's the whole idea, right? So I hope that helps. Perfect. Now let's take the next example. So here is our second example on indeterminate products. We need to evaluate the limit as x approaches 0 plus means from the right side x times ln x. So let me just sketch the graph here to understand what we are trying to figure out. So one of the graphs here is talking about x. And we are actually looking from the positive side, right? Well, that is the line, and what we are looking into as the value approaches 0 from the positive side. So we're looking at this particular point. The other graph is ln x. So ln x is kind of like this, right? So let's just draw this much. And as you can see, we are actually seeing that as it approaches 0 value, we have a situation where it is product of 0 times negative infinity, right? So again, it is an indeterminate product which we need to deal with. So as we summarized earlier, we have to convert this into a rational type of a function. I shouldn't really call it a rational function, but one over the other, right? So we'll begin with the limit as such, and we'll reorganize. So we have x times ln x. So it's a good idea to take one of them in the denominator. Only then we get 0 over 0 or infinity over infinity form. So those are our level 1 indeterminates, right? So normally the idea is to convert into those forms and then apply L'Hopital's rule. So x we could write in denominator. So I'll write this as ln x here, okay, over 1 over x, correct? So it's one and the same thing. So now you can see that ln x is approaching, as we approach 0 from the right side, is approaching negative infinity. As far as x is concerned, 1 over x. Now 1 over x will be also approaching infinity, right? So because this was approaching, right, so this will approach positive infinity, 1 over x. So we have a situation which is very well understood, where we can apply L'Hopital's rule and find the limit, correct? So that is our level A situation. So what we do here is that we convert this product and all those other cases, 7 of those, into the first 2 cases, which are 0 by 0 or infinity over infinity. So in that case, it becomes limit x approaches 0 plus derivative of ln x is 1 over x, and the derivative of 1 over x is minus 1 over x squared. Well, this could be rearranged, and I could write this as limit x approaches 0 plus, and I could write this as 1 over x. We have a negative sign, and that goes in the numerator, right? So it goes like this. So what we get here is basically just rearranging, right? Okay. So we get negative value and we get x, right? So if I substitute 0 here, what do I get? I get answer as 0. So our answer for this particular limit is indeed 0. So the answer is 0. Is that clear to you? So before applying L'Hopital's rule, we should actually try to write in a form so that we get 0 over 0 or we get infinity over infinity, and then we will really get the answer. So I hope that helps. So here is our third example on indeterminate products. We need to evaluate limit when x approaches infinity for x times ln 1 plus k over x. Now see what happens when I substitute infinity here. For x, it is infinity, and for ln, it will be ln 1 plus k over infinity, correct? Now, k over infinity means this term will be 0, right? So basically, it will be infinity times ln 1, correct? Now, ln 1 is basically 0. So we get a situation which is infinity times 0. So it's a product, right? So our approach is to write this as a ratio of functions, right? So we'll convert this into the form which is f of x over g of x, right? 1 over I should write, correct? Then we'll get our result. Perfect. So we can apply, once we do it in this form, we will apply L'Hopital's rule. So that's the whole idea. So we'll again adopt the same approach as we had been working with. So we'll now write it as ratio of two functions. We are given x times ln 1 plus k over x, correct? So let me choose to write x in the denominator as we did last time. So we have ln 1 plus k over x over 1 over x. Okay. Now we can actually, we know the situation. This is now 0 over 0, right? Approaching infinity. So this situation is 0 over 0. So now we can apply L'Hopital's rule. That is to say, we'll do derivatives on both numerator and denominator. So for ln 1 plus k over x, we get 1 over 1 plus k over x times the derivative of this, right? K times this. So which is going to be, let me write, because it involves minus k over x square. Correct? So that becomes the derivative for ln 1 plus k over x. In the denominator, 1 over x derivative will be minus 1 over x square. Now, from here, we could cancel this to simplify. So what do you get? So let's rewrite the whole expression after simplification. So we get this as equal to limit x approaches infinitely large value, and this is 1 over 1 plus k over x, correct? Here we're left with the negative sign with k there, right? So we could write this as negative, and k times 1 will be k. So we get this expression, correct? Now if I substitute infinitely large quantity here, what do I get? So let's do that. So what we get here is minus k over 1 plus k over infinity, right? So that becomes 0, right? So that becomes minus k over 1 plus 0, and that results into the answer as minus k. So in this particular case, the result is the constant. Sorry for keeping this minus. This should have cancelled here, right? So minus should have cancelled. So basically, we get plus k here. So that is the result which we get. So it is equal to a constant. So now we know that the limit when x approaches infinity for x times ln 1 plus k over x is indeed k, right? So that minus minus also cancels, so we get positive k. Now this is a very important result. We have taken actually the values with the constant. So let me write it here. We get this as equals to a constant. So there could be questions where we could actually utilize this knowledge and then solve them faster. I hope that helps. Now let's take up the last example, which involves trigonometric functions. So here is our last example on indeterminate products. We need to evaluate limit when x approaches 0 for cot 2x sine 6x. Now if I substitute 0 here, then cot 0 will approach infinitely large value, right? And sine 0 will approach 0. So we have a product of infinity and 0. So the idea here is once again to write this as ratio of functions, right? So we'll write this as ratio of functions. Correct? So the question here, which is limit when x approaches 0 for cot 2x times sine 6x, could now be written as limit x approaches 0. So cot is 1 over tan. So let's write like this. So 6x over tan x. Tan 2x. Correct? So now what we get here is 0 over 0. Correct? We get a situation which is 0 over 0. So we can apply L'Hopital's rule and then find the limit. So we get this as limit x approaches 0. And for sine 6x, the derivative is 6 times cos 6x, right? And for tan 2x, the derivative is 2 times secant square 2x. So that's what we get. Now, can we simplify this? I think we can, since secant and cosecants are reciprocal functions. So that should help us to simplify this. So let me rewrite this as limit x approaches 0. 6 divided by 2 is 3. And we have cos of 6x. And, well, we could substitute 0 here also, anyway. Or, let me write down this as cos square 2x. Okay. That's fine. So, as you can see here, if I substitute 0, we know cos 0 is 1, right? So, cos of 0 is 1, and therefore we get the answer as 3. So substituting 0 here, we get 3 times cos of 0 times cos square of 0. So those values are 1. So we get 3 as our answer. So the solution for this is that this limit is equal to 3. Perfect. So that is how you can easily find the limit for indeterminate products. So let me summarize once again that the idea here is always to write those functions as ratio of functions. So once you do that, you either get 0 over 0 form or you get infinity over infinity. Then you apply the L'Hopital's rule. Right. Sometimes you may have to repeat this rule as we saw in one of our examples. But however, you can definitely get solution in this fashion. So I hope that helps. So in the next video, we'll talk about the other forms of indeterminate. Specifically, we'll take difference of infinity. We'll take that as the next example. I hope that helps. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.